Hi, I'm William, and today we're going to talk about global issues. What do you think is the biggest problem in the world?
Worsening environmental conditions.
Starvation,
I think lack of non-renewable resources.
energy crisis,
Today, energy is a big thing. There's solar energy, nuclear energy, or even hydroelectric energy. And you know what else is energy? This pack of Lays right here contains 160 kilocalories. Calories is a unit of heat, and heat is one part of energy that is important in our daily lives. Now this relates to one big problem, that is world hunger. Now let's turn to Sedrick for more info.
Roughly 1 in 3 of global food gets wasted. That's around 1.3 billion tons of food every single year. In comparison, we have an elephant which weighs 6,000 kilograms. So that means the food that's wasted is around 260 million elephants worth of food. Now it's easy to see how this is a problem. Around 842 million people suffer from world hunger. That's more than 10% of the global population. Around 9 million people die due to hunger every year, more than malaria, tuberculosis, and AIDS combined. But this isn't just a humanitarian problem, it's also an environmental one. If food waste were a country, the amount of greenhouse gas it produces would be a lot. In fact, third most in the world, more than the entire India, and almost equal to the entire United States combined. Now, if you think this isn't present in Hong Kong, think again. 3,200 tons of food are wasted every day, and this food wastage is growing more and more. In China, 8 million tons of food were wasted by the catering industry alone. This 8 million tons is enough to feed 1.3 billion people for a year. As for where all this food comes from, it's not so clear. In our cafeteria alone, we see food waste every single day. If we estimate 300 grams of food waste a day for 10,000 people for 3 meals a day, that's around 9,000 kilograms of food waste every day. 9 tons just from one institution. The fact, however, is that most of our food waste never actually reaches our plate. If you look at this graph, you see that the food waste that comes from our consumption is actually only very little, and the majority comes from preparation and from delivery and sending the food to our plates. This is caused by all sorts of reasons, from personal irresponsibility to mismanagement of resources to overstocking, you name it. And you may think you're not part of it, and maybe you don't directly waste food, but from the process of bringing food to your table, know that food is wasted. And that food waste can be turned into something useful. And that's what we want to do. William, back to you.
I guess this is the basic idea of recycling food waste. That is to turn it into something useful, such as energy. Now with the existence of modern technology, can we run our car using food? Well, yes. And no. It really depends on how you look at it. To understand this, we should understand the basic process of recycling food waste, and that is anaerobic digestion. Now let's take a look at the thought bubble.
Now we're going to explain about anaerobic digestion.
Anaerobic digestion is a collection of processes by which microorganisms break down biomass, such as food waste or animal byproduct, in the absence of oxygen. It is used for industrial or domestic purposes, to manage waste or to produce fuels. Normal food waste decomposes and produces methane, a greenhouse gas that is 25 times more potent than carbon dioxide. In the digester, microorganisms break down the byproduct into methane-rich biogas. It works the same way as the body breaks down calories, except on a much larger scale. This is our proposed model of anaerobic digester. Our aim is to reduce odor and emissions from manure, food waste, and biosolids. Create a closed cycle for recycling organic material, and generate renewable energy. The digester will use a mix of dairy manure, dining whole food waste, and biosolids, which are nutrient-rich organic materials. Once delivered, the food waste and biosolids will be blended into a liquid solution and treated at 160 degrees Fahrenheit for 1 hour to eliminate any potential pathogens. Then, it will be pumped into the digester. The anaerobic digester is a sealed airtight tank which can hold 300,000 gallons. Organic materials will be heated to 100 degrees Fahrenheit. Inside the tank, the mixture in the digester evenly distribute microorganisms and will remain for 20 to 30 days. These microorganisms break down the mixture producing biogas and nutrient-rich digestate. Biogas, which is roughly 60% methane, is a form of renewable energy, which will be used to power up many electrical appliances, such as phone, projector, DVD player, computer, Wi-Fi router, and camera. The solid residue is being used as fertilizer, and the liquid residue is brought back to the first tank. There are 4 key stages: hydrolysis, acidogenesis, acetogenesis, and methanogenesis.
Hydrolysis. Hydrolysis involves breaking down this biomass, which is food waste, into simple sugars that can later on be processed. Now, these sugars are further broken down by fermentation into acids.
Acidogenesis. Acidogenic bacteria then convert the sugars and amino acids into carbon dioxide, hydrogen, ammonia, and organic acids.
Acetogenesis. These bacteria convert these resulting organic acids into acetic acid, carbon dioxide, hydrogen, and ammonia.
Methanogenesis. This is the only biological process. Finally, methanogens convert these products to methane and carbon dioxide. The final product contains 60 to 70% methane, which can be used for biogas. Let's turn to real-life simulation.
Hello everyone, today we're gonna give you a simulation of anaerobic digestion.
Here we have the food waste, which of course it's not actually food waste, but our research shows that processed food waste with the sludge and the bacteria, it would look something close to this. And here we have an empty bottle, but we're going to use this to represent the digester. This is where the reaction happens. Of course, in the real reaction, there will be multiple digesters and many different tanks. But for the sake of simplicity, since this is just a model, we're going to use just one bottle. And this represents methanogenesis. If you recall, that's the step where methane is produced. So the first step would be to pour the food waste into the digester. And after that, before we close the bottle, we're going to squeeze out all the air. Since this is anaerobic digestion, it happens without the presence of oxygen, hence the name anaerobic. So here we're squeezing out the air and then we're closing the bottle. So as you can see, most of the air has already been squeezed out. In the real anaerobic digestion reaction, this would have to sit for maybe like 30 days. But since this is just a model, we're going to do sort of a speed up and we're going to show what's going to happen next.
After letting the bottles sit, the bacteria broke down the food waste and produced methane. That's why the bottle will go back to its original shape.
So what we're going to do next is we're going to get this tube and we're going to connect this bottle to a bowl of water with them. So what we're if we open the bottle, the gas won't escape because as you see of the structure of the bottle. So we're going to tape the tube to the bottle now. So there, and we're going to get the other side of the tube and put it inside. And what's supposed to happen is if I press this bottle, the methane will go here and it's going to form some bubbles. So right now I'm going to And the interesting thing is, if we put the fire while this is being pressed, actually, it's going to fire up. The thing is, we're not doing it now, of course, because of safety issues. But the amount of gas that this methane produces would be able to release lots of energy and would be able to use that energy to power many things.
Now, anaerobic digestion seems great and all, but sometimes it may not be enough. Firstly, it requires the waste to be dry. Second, it has to sit in a reactor for many long time. Thus, we introduce many new innovations. Today, there's really so many ways to innovate this process. We can change the temperature, catalyst, etc. The system we propose brings the best of dry and wet of anaerobic digestion. For the dry, we use Janko and Valorga technologies. Janko is dry anaerobic composting, where the reactants are dried up and fed through the top of vertical column. Valorga is a semi-dry process. It's quite similar to Janko. For the wet anaerobic digestion, we introduce a new process called hydrothermal liquefaction and combine it with our current model. The thing is, anaerobic digestion only accepts dry waste, and although dry waste has high energy content, this means that most of the wet waste goes to landfills. In a few years, if we don't cut down on this wet waste, our landfills will soon become full. Hydrothermal liquefaction processes wet waste since it uses liquid as a medium. The interesting thing is that hydrothermal liquefaction is already in place, but usually this is used with sludge or algae and not with food. The introduction of hydrothermal liquefaction for food waste is relatively new innovation. More than that, we can also do improvements on the logistics and visibility of these systems, especially in Hong Kong, where land is a very precious resource.
So here we see a somewhat complete model of the whole process from where the feedstock enters to where the biogas exits. This, however, is too complex, so we perform mass and energy balance on a simpler model to estimate the scale and feasibility of the system that we're proposing. So here we have three equations, one to represent acidogenesis, another for acetogenesis, and the last for methanogenesis. I recall that these are the three main steps in the whole process, and so if we combine these equations, we can end up with a ratio. And this ratio is the one that we use to do the computation. And this is if we get 1 mole of C6H12O6 or glucose. This is what we see in food. Then for every mole of that, we get 4 moles of methane. And so if, for example, we can get 50 tons in of food waste a day, and let's say maybe 10% of glucose, then we have 5 million grams of glucose. Converting that to moles, we have 27,000 moles, meaning we're making around 100,000 moles of methane a day. This is of course not realistic since lots will get wasted somewhere in the middle of the process, but suppose we get 10% of that. Suppose we get 10,000 moles of methane. That's 160,000 grams divided by 656 grams per meter cubed, which is the density, and we get 250 meter cubed of biogas, which might not seem like a lot, but in fact 1 meter cube can give 6 kilowatt hours of energy. 1,500 kilowatt hours of energy, now that's enough to power a number of households, just 1 day's worth of food. As for the energy requirement, we take a look at this very simplified model, and here we see that there are two main sources of where we need energy for. One is direct energy, which is used to heat up the feedstock, and indirect energy, which is heat loss to the surroundings, and of course this is released through biogas. And in our system, we use a circular economy, meaning what's wasted, nothing's really wasted, we just put it back into the system. This is true both for the energy and for the materials.
Now, we're going to discuss about the cost of building an anaerobic digester plant based on the size, engineering, location, and waste composition aspects. There is also operating costs in running and operating the plant. Those are recruiting and paying the employees, insurance, transportation, annual licenses, pollution abatement and control, and all maintenance. For on-farm digester, the total cost including the operation costs would approximately be around 1,040,000 Hong Kong dollars to 2,060,000 Hong Kong dollars for about 3,000 tons of production per year. For larger plants, it would be more expensive and also depends on the production rate per year. It ranges from 5,416,000 Hong Kong dollars to 56,400,000 Hong Kong dollars for an average production of 80,000 tons per year. The reason why the prices differ is varies production rate. The minimum cost covers about 10,000 tons per year. Meanwhile, the maximum cost is for plants which produce about 150,000 tons of product per year. Indeed, the future of food waste processing is very bright. It holds lots of potential and provides energy for the cities of tomorrow. So, don't waste food.